Hello and welcome to video 2 of learning the Python programming language, specifically using Spider. In video 2, we're going to learn how to upload a data frame from Excel or a CSV file into Spider. We're going to learn how to use descriptive statistics and clean some data. We're going to use methods and do some method chaining. We're going to learn how to create new variables and recode existing variables. And then we're also going to learn how to compare means using independent samples t-test. Now, before we go back into Spider, I want to pull up the data set for you to get an idea of this. This is in a tidy format. So the first row is each of our variable names. Notice how each of them is only one word, and they do not start with a special character or a number. Each country is listed only once. And we have a combination of text, member, not member, number or integers, as well as floating numbers and text here. We also have a lot of missingness here. We're not going to discuss how to handle missing data for this workshop. That's a much more complex topic. So we're going to use the defaults of list-wise deletion. However, I want to mention a word of caution on that, because when you do that, if you have missing for your variables of interest, like here and here and here, if there's any missingness for our variables of interest, it's going to drop that case. So now you go from 217 countries to 217 to a much smaller subset. And that could really bias your estimates and your ability to make generalizations. So returning back to a Python script, what we're going to do is we're going to create a new object called df, which is short for data frame. From pandas, or from PD, we're using a read_CSV function. We're in our working directory for the desktop, which I have that Excel sheet already there. And I just converted to a CSV just for ease. And because the way we extracted this data set and compiled it, we need to have an encoding statement. That way it knows how to read this correctly. Sometimes you do not need this, but if you get an error that it's not coded correctly or that can't read it, you might have to try some different encoding options here. And the easiest way to do that is actually just type in Python encoding, and it has a list of different ones you can try out and see what works. So I'm going to go ahead and create a new data frame, a new object. We have df, a data frame, which has 217 observations of 13 variables, and then it lists our specific columns. If I use df and print that out, it's going to concatenate this a little bit and truncate it actually. So we'll have those jumps, and it will also, it'll show you the first, the last, and as well as position number. So position 0 is Afghanistan, and so forth. Now what we can also do is we can use things like print, or print out the first 5 observations and the last 5. So if we say, okay, object.head, so running the head and then kind of specifying how many observations, so I want the top 5 cases on our df data frame. So when I do that, it gives 0, 1, 2, 3, 4, our first 5 observations, and it gives a little snapshot of the information from the data frame. We can also do tail, and that gives us the last 5, and you can actually change this from 5 to, let's say we wanted 15, so it's quite flexible. We can also do df.info and leave that blank there, and that'll provide information such as the range, the position number, the object type, so it's a pandas core data frame type, the data columns, that there's 13 of them, list each of the 13 different columns, and the type says we have an object, non-null, we have a floating, a couple more floatings, and so forth. We can also use the select feature, which is really helpful. So select is essentially, we're saying from the data frame, select country and give me and run head 5. So it's going to print the first 5 just for the variable country. You can do the same thing on corrupt or for literacy. All the same thing. Let's say that you wanted multiple columns. What we can do then is we can create a list. Yeah, we're going to create a list called select. And we're going to list out our variables of interest. So we're creating an object that's a list of variable names or column names. And we're saying df select. So it's going to go ahead and import all three of those variable names in here. We do head of file and print out just those three columns for the top of our df. So essentially you're not really subsetting the data, but using it as a selector to then print it out. We can also do things like print out the frequencies for the variable of free new, which is the types of democracy for this. So we're going to assign this called free count, saying, okay, for this variable in df, free new, give me the counts for each of the different ones in there. So if we go ahead and do that, we now have a variable called free counts. And if we print that out, how many countries are considered free, how many are partly free, how many are not free. One thing I want to show too is if we click on the df and double click on it, this gives us a nice little visual. So we can actually remove the background color to make it easier to read. But we see that as the OECD member, so it read that text in. We have NAN is missing. Those are all missing values. And then lower scores and higher scores comparatively. So the min and the max. Great. Now with our free count, now that with the frequencies in there, I'm going to go ahead and refer to that object and do a dot plot and specify kind is going to be a bar chart. So now we have from matplotlib a bar chart for the frequencies of how many countries are free, partly free, or not free. We can also do things like crosstabs. So how many countries are, whether or not they're an OECD member, and compared to a table of the free. I'm going to do margins here too. So I'm going to go ahead and run line 104. So now we get a breakdown of how many, all of the countries that are free, all not free, all partly free. So going down, as well as across for OECD membership, and how many countries fall within each, like not free and a member, partly free and a member, free and not a member. So you can see the breakdown of this. Now what we're going to do is we're also going to use what's called using multiple methods in the same command, sometimes called chaining methods. The command below is going to pull the variables we have in the select list we made previously. We're going to then sort the values based on perceived corruption scores. Ascending equals false, so it's going to be descending, and then print the top 15. So we have our least corrupt perceived corruption countries going down. And we've used our select subset essentially too. We can also set up conditional statements. So if you want to use like if they have a score equals to like equals not free or not equal to. So if you want equals, that's saying it's specifically that value. If you have an exclamation point equals, that's not equal to. You can do greater than, less than, and so forth. So what I'm going to do is I'm going to create an object saying from the df data frame, if any of the values under free underscore new are not free, we're assigning it to mask, and then doing df and using that subset. So pull those that meet that condition. So now we have a list, or not a list, we have a subset of the data that meet that criteria. You can actually assign that to a new data frame if you want to. We can pull all the countries that have a literacy rate higher than 99 and assign that to mask 2. Then look at that subset. You can also run a query. So within this, I'm using df.query. So that's going to be the method saying country. You notice how we have single quotes inside double quotes. We're using, okay, if the country is China, and then saying country equals equals. So we need to start and end with the same ones. If we rotated this and change it around, it would be an error message. So we run a df query. If it's trying to, that's going to return that single observation in our data set. Now we can actually go ahead and we can recode a variable. As we mentioned earlier, corrupt is actually reverse coded, so higher corruption scores reflect a lower perceived corruption. Now we want to reverse this, so then higher scores actually reflect higher perceived corruption, and then say that as a new variable called corrupt2. So we're saying, okay, df, we're creating a new variable, a new column called corrupt2, and that's going to be assigned 10 minus each country's corruption score. So if they have a 10, it's going to become a 0. If the country has a 9, it's going to be flipped to a 1, and so forth. This is a quick way to do a reverse code. What we can also do is we can recode continuous variables into a discrete variable. Sometimes you may want to turn a continuous variable into a categorical one, such as low, medium, and high variable. This makes it a little bit more easier to interpret. However, that does come at a cost. Let's say we have a country with a 3.4 and a let's say it's actually a 6.5. So even though they might be at separate parts of a bin, we're saying treat them as essentially equal. So we lose variability there. What we're going to do is we're going to create a function here. We're calling this function categ. It's going to be a series. And then saying if series, so whatever the variable that's in there is going to be, if it's less than 3.4, return a low. elif, which is else if it's 3.4, if the series is greater than or equal to that, but it's less than a 6.7, return a medium. Then elif, or else if it's equal to or greater than 6.7, but less than 10.1, again, our top variable here is 10, we want to make sure that we're catching that one, return a high. So we're going to highlight this whole thing. We're creating this function. Okay, now we have to run the function. So we're saying, okay, we're creating a new variable called corrupt categ in our df data frame. And that's going to be a function of corruption2, and we're going to apply our function to that variable. And that's going to go ahead, and that's going to, if we go back to our data frame, if I scroll over, we have our corrupt2. We maximize this. So here's our original corruption2. If we add those together, it has to equal the maximum, which is 10. Well, based on the 7.5, they should actually be in the high. And here's our high low. And none essentially means it's missing. So we didn't have that information there. Now, if we do a value counts, sort by true, on corruption categ, when we return that, that's going to give our frequencies. Great. So what we're going to do now is we're going to run some descriptive statistics. So if we get we're going to run the mean function on our data frame, specifically corruption2. I want to get the mean for that. It's going to run in, say, NaN. This is because we have missing observations. So what we need to do is we need to drop cases that have missing values for those that we want to run this with. So what I'm going to do is I'm going to create a new variable, or a new data frame called dfcomp. dfcomplete is what it stands for. And we're going to say, okay, df, so we're using a drop NA function on our df data frame. So if there's any missingness for the subset or for the variables GDPPC or corruption2, drop it. And store all those ones that weren't dropped into a df complete. Now you can see we have a reduction of sample size from 217 to 151. Now if we run our mean for corruption2 using our new clean data set, we have our mean, which is 5.89. Our mean corruption, or mean GDPPC, is 11,320. Our median, so we can actually use the median function on both and report those. What's our middle number? And again, we pulled these from our statistics. We imported these specific functions. We can also do df complete, the specific variable, then the .std function, and that's going to return standard deviation. We can also get the variance, for both variables. And we can also, from SP, we can use SP skew. That was so kind of looking at the skewness. So how being pulled in one direction or another are the potential outliers. And look at kurtosis. So what's the normality? Is it a normal curve, which would be 0? Is it a really flat distribution, or is it a really peaked distribution? Now, an alternative method is just to refer to the data frame in the variable, then using a dot describe. That's going to provide the counts, so how many observations do you have, the mean, the standard deviation, the minimum, maximum, and the quartile splits. We can do the same thing for GDPPC. What I do now is we're going to run a t-test. So here we're going to try to determine whether GDPPC differs based on the corruption categories that we created earlier. We're going to start by subsetting the data, so we have a subset of data for each of the 3 categories and saving them as separate objects or data frames. So what I do is I'm going to say, okay, df complete. If df complete, the corruption category is low, store that object as low corruption. We'll do the same thing for if it's medium or if it's high. So now we've created 3 different subsets. Now, a t-test is the most basic way to compare 2 groups on their mean scores on a single outcome variable. While we divided corruption 2 into 3 groups, we can only compare 2 of these groups at a time using a t-test. So we're going to compare the low group with the medium group and see, are there statistically significant differences? The first thing we need to do is we need to check the underlying assumption that variability in GDPPC in the low group and in the medium group that are not statistically significantly different from one another. This is called the test of homogeneity of variances, or Levene's test. If the p-value is less than 0.050, then we violated that assumption. The null is that there is no statistically significant differences in the variances. If there are, if we reject that null hypothesis, we need to use a correction to account for that violation. So we're going to go use SP, so we're using the Levene function, looking at our 2 separate groups, and our outcome variables are GDPPC, and storing that as Levene. I'm going to go ahead and print that. So these are the results. Our statistic is 0.339. Our p-value is 0.562 with rounding. Based on this, we failed to reject the null hypothesis. So there are no statistically significant differences in the variability between these groups. So we're safe to go ahead and use the t-test. So in 175, we're going to go ahead and do an independent samples t-test. That's sp.t-test_ind. That's for independent. We have our first group and our second group. X is 0. I'm going to use equal variances equals true. If we violated this assumption, then we would change that equal var to false. So I'm going to go ahead and run that, and this is our result. Our t-statistic is 9.87. Our p-value is 0.00000, because we have scientific notation to the 15th decimal. Now, we're missing an important feature here. We're missing the degrees of freedom. So what we're going to do now is we're going to calculate that. So we're going to use the LEN mode to calculate what's the sample size of each group. So let's just go ahead and do that. So we're going to get the DF for the low group, DF for the medium group. We want to calculate degrees of freedom of adding the 2 lengths together in -2, because we have 2 groups. So we have 72 degrees of freedom. So now we have everything we need, and there are statistically significant differences in the means between these 2 groups. We're going to stop this video here, and next we're going to cover scatter plots, correlation, simple regression, and multiple regression. See you at the next video.